So we've been looking at some of the challenges of being able to point to causal relationships when looking at observational data. And this is sort of different than experimental data where I was able to control where people were placed in what groups. I was able to assign a treatment. With observational data, we're sort of taking what we see in the world, and what the world gives us is oftentimes messy, and it requires us as statisticians and as social scientists and as critical thinkers to kind of tease out how different patterns are sort of interrelated, and hence sort of how that selection process might complicate the story we're trying to tell. And so as part of that, I'm going to sort of look at four different fallacies or paradoxes that pop up in observing and studying observational data to kind of reinforce really the challenge of doing this well. And so I'll begin with probably one of the best known of these paradoxes, which is Simpsons Paradox, which is sometimes called the lurking variable problem. And this is really sort of the foundational piece behind all of regression analysis and multivariate regression, that we're trying to solve the lurking variable problem or resolve the lurking variable problem. This is basically a problem that comes up when we're taking different groups of cases that are categorically different or even just continuously different. They change sort of gradually along a dimension, and we lump them together into a single analysis, and we look for a pattern within those groups of cases, and we find something that seems to be a fairly straightforward story. So this is made up data, but it's not completely made up. I did a deep dive into the effect of negative advertising on campaigns a number of years ago, and was sort of interested by the lurking variable problem that was going on. So if you just look at the headline of how do candidates do when they run ads versus not running negative ads, what you find is that candidates that don't run negative ads seem like they're doing better. And that one interpretation of that is that negative ads really turn voters off. They don't like candidates who go negative, and therefore they vote for them in smaller numbers. And while that maybe is soothing to how some voters like to think of themselves in terms of their civic engagement and their sort of interest in the issues at hand, that's actually not how political consultants understand campaigns, and the value of going negative comes up time and time again. And so when I saw that first sort of headline number that candidates who choose to run negative ads do worse than candidates who don't, I thought maybe there's a lurking variable in here that explains that pattern. And sure enough, when I dug in, what we found is that, well, nobody just sort of randomly decides to run negative ads. Negative ads end up being run when you get races that are really competitive, right? That when you have a competitive race, you feel like you need to do something to run to close the gap, and so, or not close the gap, to pull ahead, and so you might be more inclined to run negative ads. And when you are the trailing candidate in a non-competitive race, running a negative ad is something that you can do to kind of push yourself ahead. And so when you kind of break it down that way, what we find is that situations where we don't see negative ads run tend to be situations in which we have a candidate who's going to win and win decisively, and so they're racking up a very large percentage of the vote share. Where we do see negative ads are when we have a person who is likely to lose unless they do something, to tear down the leader, right? So we get negative ads associated with lower vote shares, and we get negative ads occurring in competitive races where the candidates are basically tied. And so when we separate that out, the story of running negative ads hurts you completely falls apart, and in fact kind of reverses. It turns out that you're almost always better off running negative ads and trying to tear down your opponent, because you'll do better than you might have done otherwise. That's an example of the lurking variable problem, that what we see as sort of the headline story reverses when we separate out different situations that are actually being lumped together within our data. And so one of the things that we really work on with regression analysis is trying to find the appropriate variables to add into our models, so that we're able to say in a convincing way, there are things that are probably intertwined here that make these cases different, but I've controlled for them in a statistical sense. And we've talked about that a little bit earlier on. So Simpsons paradox and the lurking variable problem is a really critical thing, and we have a good strategy to deal with that. What we don't have as good a strategy to deal with is Bergson's paradox, which is sometimes called the collider problem, which is not that there's necessarily a lurking variable that we can find that it will suddenly magically explain everything and it will all make sense and we'll be like, oh, that squares with reality. Instead, the collider problem of Bergson's paradox comes from a selection process that determines what we see in terms of the cases we're observing and where we're looking for a pattern. And this is something that's been widely talked about recently because there's been some weird COVID findings about how if you look at hospitals, people who smoke seem to do better with COVID than people who don't smoke, which seems really counterintuitive for a respiratory disease. And people who've dug into it have said, no, it's actually a collider problem. And I had a hard time wrapping my head around that until I saw this example about GPA and SAT. And so at a particular school, we might observe a negative relationship between GPAs and SATs, that the better your SAT score, the worse your GPA score is likely to be. And that seems really counterintuitive. Normally we would assume that GPA and SAT would be sort of positively correlated, that they're both picking up something about studiousness of individuals. But it turns out that there's a reason why we see that negative correlation for that school that has to do with how that school is selecting their applicants or their students, right? And so they have a formula in which you can, where they add GPA and SAT scores together and take students who pass a certain threshold. And so if you have a low GPA score, but a high SAT score, you can be admitted. If you have a low SAT score, but your GPA is really strong, you can be admitted. And students who get both high GPAs and high SAT scores tend to go elsewhere. And so they're not showing up. Those are the pink dots in the upper sort of right-hand quadrant. They're going elsewhere, and so they're not showing up in your sample. And folks who don't have a high GPA or a high SAT, they're not being admitted. And so they're not showing up in your sample. And so because of a selection process that we've imposed on our data collection, we've created a situation in which we're looking at a not necessarily representative sample of the larger pattern. And within that non-representative sample, because of how we've selected cases in, we're observing this sort of negative relationship where in the larger world, it's a positive relationship. And I don't necessarily know if there's an easy way to fix that in a statistical sense. In fact, there's not. The only thing that I can say is when you get a weird pattern that doesn't square with your overall understanding of the world, we should always sort of step back and ask, is there a weird selection process that's driving this, that's creating my pool of cases in a way that's not representative, and in fact is possibly truncating out people on the lower end or people on the higher end, so that I'm getting in sort of this collider problem popping up in my analysis. And other than critical thinking, I don't really have a solution for this. Maybe more advanced statisticians do, but I think critical thinking is the starting point for dealing with this one. Okay, so we have a third, well, I guess this isn't really a paradox so much as a fallacy, but I think when it was first introduced, it was kind of understood almost more as a paradox. This is the ecological inference problem, or the ecological fallacy, which I'll describe it, I'll give you an example, and then I'll describe it in a slightly different way. So what it means is that when we find patterns at the aggregate level, those patterns might not be true at the individual level. Okay, so the example that first broke this open, although I've heard dozens of examples over the years of places where this plays out, is in the 1930 census. It was shown that areas with higher immigration had higher literacy rates. And this struck people as very bizarre because the assumption in the 1930s was that people who were immigrating in were coming in from very poor regions, primarily of Europe, and didn't have access to primary school and therefore had lower literacy rates than the larger population. And yet, how could this be? We have cities, they have more immigrants, and they have higher literacy rates. Does that mean that, in fact, counter to our expectations, immigrants coming in had higher literacy rates and therefore were raising the average? And that's not what was happening. What was happening is, sure enough, if you look at individuals who are migrating in or immigrating in, they had, on average, lower literacy rates than the average population within the United States. However, the average population across the United States was not sort of evenly distributed in literacy rates. Literacy rates tended to be highest in cities where there were functioning school systems, and they were lowest in rural areas where access to school wasn't as easy or wasn't as universal. And so what you end up having is, because of a choice made by immigrants about where to immigrate, immigrating to high literacy areas, sure enough, places that had higher literacy rates also had higher portions of immigrants. And so we can't necessarily draw correlations about what's happening with individuals, high literacy rates, lower literacy rates for individuals, based on patterns we observe at the aggregate level. And this is sometimes thought about as a unit of analysis problem. And that as long as your unit of analysis remains consistent, you should be fine in drawing conclusions. What that means is, if I'm collecting data on individuals, I can say something about individuals. If I'm collecting information on literacy rates of immigrants and non-immigrants, I can say something about the literacy rates of immigrants and non-immigrants. But if I'm collecting data about aggregate literacy rates in cities or school districts or regions, I can't really say anything about the people within those regions. All I can say is, these regions have higher literacy rates than those regions. And I am not in a position to tell you why that is, because there's messiness that might be involved. I'll give we'll talk about a second unit of analysis problem, but I think as long as we hold to that basic principle, what is it that I'm looking at? Individuals, cities, counties, states, whatever it is I'm looking at, that's where I can limit my generalizations to. I can talk about individuals. If I'm looking at individuals, I can talk about states if I'm looking at states. And if I stray off of that, I am potentially going to be making an ecological inference fallacy. There's a slightly different inverted version of this, which sometimes is called the reductionist fallacy, although I think people use the reductionist fallacy in a slightly different way than statisticians do. Sometimes it's used to say you're taking incredibly complicated things and boiling them down to just a simple narrative that doesn't really capture the complexity of it all. But in this case, we're talking about a second unit of analysis problem, and that is where we're collecting data on individuals and we're making a jump to what's happening at the aggregate level. So it's the inverse of the ecological inference problem. We're collecting at the aggregate level and trying to make conclusions about individuals. And so I've been struggling over the years to find sort of a good example of this. And I think one example came out of a long-running fight I've had with a colleague, Andy Hultquist, about whether or not we should believe what people give us in surveys. And I tend to believe that if you want to know what people's preferences are, you ask them. And Andy Hultquist's view is that if you want to understand what people's preferences are, watch their behavior. That people will tell you what is true with what they do, with what they want, with what they do. And the crux of our fight really boils down to this reductionist fallacy piece. And I'll give you an example that I felt was particularly convincing in my debate and argument with Professor Hultquist. So what I argued is, if you have a school bus company, right, and they want to know what the demand is for children going to a new school district that's just been built, or a new school that's just been built in a new neighborhood, and they survey residents over the summer, do you think your kids should walk to school? And he used the word should, like, should they walk to school? And the school bus company finds that the overwhelming number of people that they survey say, yes, I want children to be walking to school, as part of their day, and and therefore the conclusion would be they're not going to take the school bus, and the school bus company sort of assumes that people won't be using their services. And yet when the school year starts, there's massive demand for the school bus, and the school bus company is like, well, what is going on here? And concludes that people are lying, that they in that survey they were lying, and what we really need to do is we need to look at their behavior. And I sort of tugged at that and said, well, so let's look at that in a different way. You wanted to know what people's individual preferences were. I want my child to walk to school. But I'm not making that decision about whether I actually have my children walk to school in a vacuum. I'm making that in the context of a community and a neighborhood. And while I thought I wanted my children to walk to school, when I look outside, I see that nobody else is sending their kids to school. And I don't want my child to be the only one walking alone to school. If it's a parade of children going to school, I feel a little safer about that. I feel like cars are going to be aware that they're going to drive slower. I feel like there's safety in numbers. I feel like I can trust that if my child gets hurt on the way, one other child will help them or call for help. Right. So if I'm looking out the door and I don't see any other children walking, I'm going to make the choice. I drive my child to school, or they take the school bus. And so essentially, when we're faced with operating in a actual larger collective social environment, our behavior might reflect what other people are doing as we try to norm to that, rather than what I individually want to do. And what the reductionist fallacy is getting at is we can't really understand what's going to happen when you put a bunch of people together based on our analysis of them as individuals, because that together piece and how they interact is important and can change and create a different kind of pattern than what you would anticipate looking at the individuals. And so again, it's another example of the unit of analysis problem, that when you collect data on one unit, individuals, we can't draw conclusions about another unit, neighborhoods, school districts, cities, counties, states, countries. It just doesn't work that way. And even if it seems occasionally like it will, we always run the risk of bumping up and against one of these fallacies or paradoxes or drawing incorrect conclusions.